Okay, so today we're going to go over a solution of a differential equation using Euler's method, or as I always try to call it, Euler's method. But it is Euler's method. So today we're looking at the differential equation dy dx equals the cotangent of x times y. And so in order to look at that, we don't have any tools to be able to find a solution to that differential equation. I don't have any tools to do it, and in fact, I looked on Wolfram Alpha and a few other sites to see if I could find a particular solution at our initial values to compare our Euler's method solution to see how accurate our solution really was. And I didn't find any particular solutions that actually came out of those sites. So I think that in our toolbox, the only way that we know how to solve this would be by using Euler's method. Our initial points here that we've chosen are y equals 0.5, or y of 0.5 equals 1.5. So we need to find the corresponding y value at x equals 2.5 given those initial values. So what I've gone ahead and generated here was a direction field for the cotangent of x times y, and you can see that we have our little solution curve sketched in here following the direction field. So at the initial point here, we can start to draw our solution curve following the red line, and you can see that we followed the arrows up and then we come down a little bit, and we eventually arrive at our second point here at 2.5 comma some y value. And I've come over here and approximated that y value to be equal to 0.75. So we'll see what our Euler's method solution yields as a result. So in order to set up the Euler's method, I used the same table we did in our online lectures, and the same method. I don't know if there's a different way to approach Euler's method, but this is the one that we learned. So you can fix a delta x, and so that's what I've done up top as part of the setup. So our delta x is equal to 0.5. So the way to approach Euler's method is to set up this table of values, set up an x and y column, set up a dy dx column, set up a delta y column, and then finally a new y column. And so the method by which you approach this table is to take your initial points, which I'll highlight here, your initial points, and you take those points and plug them into the function that you have in your differential equation. So the function we have is the cotangent of x times y. So you take your x value and your y value, multiply them together, and you plug them into the function cotangent. For this specific example, that's the procedure. And so for our first dy dx, it's equal to, or approximated as, 1.07343. So I've chosen to keep 5 digits of precision through this whole problem. And so the only column where you can really say that it's equal to the value that you are calculating is this column, and it's only equal to that this value that we calculate up to 5 digits of precision, right? These other values are approximated, but since we're limiting ourselves to 5 digits of precision, we can say that this is equal to 2.03671. But let's go back and continue on through our first row here. Our first row continues as highlighted in yellow. So we've just calculated our dy dx. So now we need to calculate delta y. Our delta y is dy dx times delta x, which we have set as 0.5. We did that in the beginning of the problem. So our dy dx, which we just calculated, multiplied by 1/2 gives you 0.53671. Next, you need to add your delta y to the existing y, which for the first line came from our initial conditions way up here. So our initial y value was 1.5, and now we add our delta y, which we calculated, to that, and we come up with 2.03671. And so we can see what's happening here. We look at our solution graph, and we see that at our x value of 0.5, okay, that's our new y value. So we come up and we can see that the new y value is high. So the fact that it's high shows that our Euler's method solution is starting high, way up here, and we're gonna slowly follow this curve as we come down, and we'll probably stay above the curve the entire time that we're following it, and it shows us that it is just an approximation. It's not quite an initial. It's not quite a particular solution, right? So we'll come down and we'll take our new y value, which we've just calculated, and we'll come down into line 2, which I'll highlight here in orange. So our x value is now stepped by our delta x. So we started at 0.5, we step it by 0.5, and we see that our new x value is 1. We take our calculated new y and plug that in for our y coordinate down here. So we follow along in the second line using the same procedure as we did in the first line. dy dx equals the cotangent of our new x and y values multiplied together. And so I've approximated that value as negative 0.50283, which at first did freak me out a little bit. We have a dy dx and it came out as a negative number. But if you think about that for a moment, if we look at our graph, if we follow up from 1, we can see that at that point, where that intersects our solution curve is where things start to turn and become a negative slope. And so I'll say this a few times, I think, but if our graph was drawn just a little bit better, we could see that this is starting to become a negative slope, just a little bit. So a negative half for our slope is not necessarily wrong or a bad thing. So we're moving through, and we're going to continue to see how that negative slope plays in and how accurate our solution comes out at the end. So our delta y that we calculate from this information is half of the dy dx. So that's negative 0.25142. Then we plug in, we add our existing y, which conveniently now is just right above this value, and we add that to our delta y. So delta y plus the existing y value, which gives us this value here, 1.78529. And so if we come back over here to our solution curve, 1.78, we'll round that out, and it'll be right about here. And so you can see that our solution curve is starting to look a little bit similar to, but higher up than our solution curve that we've drawn in, given our initial point and the direction field. So we're following along, and we're still a little bit high. You can see that it might start to tend down towards our solution like that. But we'll see what happens as we go forward. So in a new color now, let's see, green. Sure. We take our y value that we just calculated. Again, now we're going to step our x value by the 1/2. So now we're up to 1.5. And we plug in our y value, which we just calculated, as the new y value here. Dy dx, cotangent of x times y, again yields a negative value. This time it's a little bit steeper. And if we hop back over and look at our solution curve again, we can see that this is where the slope is becoming a little bit steeper. So if we trace this up, I'll use a straight line here. If we trace this up to our solution curve, we can see that the slope is steeper now than it was here at this point. So we can expect a greater, well, more negative number. If we take the absolute value, it would be a larger number, right? The slope is more extreme. So we come back over here and we're going to follow through and complete the same process. Our delta y, which is dy dx times delta x. If this value here as the negative 1.999 was almost -2, it makes sense. This is -1, and we move forward, plug that value into this procedure here where you're adding your existing y, again here, to the new delta y, which you just calculated. That comes out as 0.78531. So now we're coming into our solution curve, and we will see 0.78531 is slightly low. 0.78531 is somewhere down here. So we're following along and connecting these values, and we can imagine now that the Euler's method solution was high. Now it's falling low, and we'll see where we end up in the end. And again, this is an approximation using large steps. So I suppose actually that these connections between the Euler's method points should be linear. They're averages over those steps. So we started at 2 point some value. What was that? 2.03, and we came down to 1.78. So let's see what that step looks like here. Let's call that this step. And then our next step was down linear now to our 0.78531, which is highlighted in green over here. Put a star next to it. So now those two linear connections are formed. We'll see what our next linear connection looks like, where that takes us as far as the Euler's method curve, and we can compare that to our approximated value of 0.75. So we'll follow through, select a new color here. We'll go with, let's go with blue this time. I like blue. We'll step our x value by 1/2 up to 2, plug in our existing, or not existing, our calculated y value from the previous step. Our dy dx now becomes quite small, and that makes sense if we look at our solution curve. We're starting to level out in this section between 2 and 2.5. Our y value is 2 here. So if we come back over and look, our solution curve is starting to level out, and the slope is tending towards 0. And again, if my graph was drawn just a little bit better or a little bit more accurately, you might see that a little bit better than we do in this curve. So we'll continue through the solution. Our delta y becomes, again, quite small. It's 1/2 of our dy dx. And then you take that delta y and you add it to the y from the previous step, which in this case makes almost no difference. And you come up with 0.78540. So our final point And the point of interest for us, in fact, let's use like a really bright color here. Let's go with pink. Our point of interest, which we care about, is their 2.5 x value, and we get a y value of 0.78540. So we'll come over here and we'll compare that to where we landed here. So we can see that that would be just a little bit higher than our 0.75, again with a linear connection between those 2 points. And so overall, our error for this problem would be represented in this area here, and we'll continue that down, and this area here. It's the difference between the Euler's method curve here and here, and our solution curve that we drew before, which is represented here. So as we were calculating error down below, remember what this error field looks like, which we've just kind of put in slashes, and we'll compare that. How large is that, the positive region up here compared to this negative region down here, and we'll see how close we actually got. So using our approximated value from Euler's method and the direction field, we can calculate an error over here. So our error ends up being quite small, 0.03540. At least in my opinion, that's quite small. Almost 4/100ths, which depending on your application could be huge, I suppose. But our Euler's method result shown here, and our direction field approximation shown here, the error comes out to be quite small. So a linear Euler's method approximation comes out not too far from a graphical tool, which if you have a graphical tool can be quite powerful, but again is not necessarily mathematically backed to the precision that you might need to carry through a given application. So I think that's all for this. Thank you.